Black body radiation, one of the important characteristics of electromagnetic radiation. Okay, it was observed by Max Planck in 1901. Okay, he observed the distribution of energy in the spectrum of heat radiation emitted by hot body. Okay, so black body radiation we can observe in the case of hot bodies. They emit certain types of radiations when heated. Okay, when solids are heated, when solids are heated, they emit or absorb, they emit or absorb radiations over a wide range of wavelengths. Okay. For example, in the case of an iron rod, when we heat this iron rod, at first we can see that the color of the iron rod turns dull red. Okay, if we again increase the temperature, it turns dark red. Okay, now if we increase the temperature again, it turns white in color. Increase the temperature, turns white in color. Okay, and at a very high temperature, the color turns blue. Okay, from this we can observe that if we increase the temperature, okay, radiations of different wavelengths are emitted. Okay, this is observed by the Max Planck. Okay, and we can observe that this as the temperature increases, the frequency of the radiation also changes. That is, the changes is from red to blue. That is, we can see as the temperature increases from lower frequency to higher frequency, emitted radiation varies. Okay, the radiation emitted varies from lower frequency region to the higher frequency region in the electromagnetic spectrum. That is why the iron rod changes its color from red to blue at a very high temperature. Okay, now what is a black body? It is an ideal body which can emits or absorbs all radiations of different frequencies fall on it. Okay, all radiations of different frequencies fall on it. Okay, so we can say black body is a perfect absorber or a perfect emitter. Okay, but this is only a hypothetical concept. Such a body is never seen in the anywhere. Okay, next, the exact frequency distribution from a black body also depends upon its temperature. Okay, frequency distribution of emitted radiations from a black body also depends upon radiations from a black body depends upon the temperature. Now let us draw a graph which shows the relationship between the wavelength or frequency, wavelength and intensity of radiation. Okay. This is the graph represents intensity of radiation versus wavelength. Okay. So from this graph we can observe that as lambda increases, intensity reaches a maximum and then starts decreasing. Okay. At two different temperatures we will obtain two different graphs. Okay. Here T2 the temperature is greater than T1. Okay. If we take lambda m is the maximum value at which the maximum lambda at which the intensity of radiation is maximum. Similarly, in the T2 also lambda m represents the maximum lambda value at which intensity of radiation is maximum. And when we observe this graph, we can see that lambda m shifts towards the lesser wavelength region as the temperature increases. Here T2 is greater than T1. So lambda m shifts towards the lesser wavelength. So we can observe that lambda m is inversely proportional to temperature. Okay. So Planck's quantum theory can also explain the distribution of intensity of radiation from a black body as a function of lambda with different temperature at different temperatures. Okay.